So when looking at an operational amplifier, we typically see a symbol for an operational amplifier that has a couple of supply rails, a plus VDD and a minus VDD. We have a single-ended output, V out, and we have two inputs, a non-inverting terminal and an inverting terminal. Oftentimes you'll just see this drawn with the much simpler symbol where we just have the inputs and the output. Knowing that our operational amplifier has a limited supply voltage range. So looking at our operational amplifier equivalent circuit, we might see a symbol where we have an input terminal, our inverting terminal, another input terminal, our non-inverting terminal, and we show this with a broken connection to represent that we want a very high or infinite input impedance. We put an input voltage V1 on one terminal, an input voltage V2 on a second terminal. Internal to the operational amplifier, we have a voltage-dependent voltage source. And the voltage-dependent voltage source is equal to A times whatever is on the non-inverting terminal minus whatever is on the inverting terminal. And of course, our ideal amplifier has an R out is equal to 0 and an R in differentially that's equal to infinity. So in this case, if this is our output terminal, we could write that V out is equal to A times V plus minus V minus, or is equal to A times V2 minus V1. So we're amplifying the difference between the input and output terminal. One way that we might model an operational amplifier in a simulation is to use what we call a VCVS, a voltage-controlled voltage source. And our voltage-controlled voltage source has two inputs. We might label one V1 and V2. It has some input resistance, and it has a voltage-controlled gain, AV, that we take our output from. So in simulations, sometimes we can use this for a simple operational amplifier. Alright, so thinking about the properties of an ideal op-amp, we can now start to list these. So we know that our input resistance is equal to infinity, and this leads to our second property. If our input resistance is equal to infinity, that would mean that the current flowing into the terminals I minus and I plus is equal to 0. Of course, we know that our output resistance is equal to 0. We would like our voltage gain to be infinite, ideally, and we get to a fifth property that says that V plus is going to be equal to V minus when we connect the system into in feedback. Thinking about this, let's assume that we want the output voltage to be finite from our operational amplifier. In other words, we want it bound by something. If we had A is equal to V plus minus V minus. And we know that AV is equal to V plus minus V minus. And we know that AV we desire to be infinity. Then this would equal infinity. And we don't want an infinite output, so the only way that we can make this an infinite output is to have V plus minus V minus equal to 0, in which case what we mean here is that V plus is equal to V minus. And in fact, what's going to happen with an operational amplifier is that we're going to place feedback around the amplifier, and the feedback will force the two inputs to be equal, assuming that the amplifier has very large or nearly infinite gain. So let's look at a negative feedback system in the next set of slides.